Good morning. Welcome to NPTEL course Transfer Phenomena in Bioprocess Engineering, week 3. Last class we discussed about the fluid flow through circular tube. Now the continuation will be here. So the Hagen-Poiseuille equation, we already discussed what is Hagen-Poiseuille equation, where we use this one. Normally we use the laminar flow system, the Hagen-Poiseuille equation. But sometimes will give error also, because this equation, some various calculation, there may be give some error due to that for developing or exiting flow at both end of pipes. No. So definitely then we have to modify the based on the real situation, we have to modify the equation, we have to modify the laminar flow Hagen-Poiseuille equation. So what is the friction factor here? The friction factor is the dimensionless number which provides an idea about the magnitude of shear stress produced by the solid boundary as a fluid flow. So commonly we use for laminar and especially in turbulent flow is called as a fanning friction factor, that is called F fanning friction factor. So friction factor definition here, F equal to the basically the ratio of shear stress at the wall and then the kinetic energy of the fluid, whatever fluid you are using here. So here tau is a shear force per unit area on the wall of the tube, then the rho is the density of the fluid, then V is the average velocity of the fluid. Whether it is a dimensionless number, we have to check. F equal to tau shear stress, that is the Newton per meter square. So the rho is a kg per meter cube density, then velocity here meter per second. So here what we have to do, the Newton per meter square, we can write Newton is a mass into acceleration. So mass kg into acceleration meter per second square. So then 1 by of meter square. Same here kg meter per meter cube second. So if we get a cancel, then we will get a finally is a dimensionless numbers. It's called a dimensionless numbers. The meter will get cancelled. So meter second square. So finally we will get the it's a dimensionless numbers. We always say it's a dimensionless numbers. There is a no unit for this one friction factor. Okay. This one the tau shear stress. The shear stress is the shear ratio of the shear force per unit area. Then the density is here, then velocity is here. Okay. So this is a meter square per second square, because V square, I am sorry, here meter square per second square. So that then finally this will be a kg meter second square, same way here also kg meter square, you get finally 1, it's a dimensionless numbers. We know that the fluid circular, for flow of the fluid in the circular tube, tau into shear, the area, tau into pi dl into pressure drop into circular this one area. So that we then after the modification, because this is equation 2, for equation 1 we know what is equation 1. Equation 1 is F equal to tau by rho of V square by 2. So substitute here tau equal to, instead of substitute the F rho V square to here, then we get a cancel here, then finally we get a friction factor of the fanning equation. So here we can see here the tau equal to rho V square by 2 of then pi dl equal to then delta P pi d square by 4. Just pi will get cancelled, then the dd also will get cancelled. So after that we will get this equation. It's a fanning equation. This is known as a fanning equation. It's always use the pressure drop that occurs in the when liquid in the flow of pipes. Flow in the pipes, there is a pressure drop will be there. There we have to use the friction factor, the fanning friction factors. So the friction factor, basically two type of flow is there. One is the Reynolds number. Based on this equation, only depends on the Reynolds number, whether it is a laminar flow or turbulent flow. So the friction factor normally it's a function of the F is a function of NRE, Reynolds number, then the roughness factors. So, the Moody chart experimental results are plotted showing the, because there is a chart is there, from there we get the we can get the value of what is the friction factor value. So, then normally the plot with the F versus NRE. So, we will get where exactly our this one the friction factor exactly based on the Reynolds number, whether it is a laminar flow or terminal flow, this one. The Reynolds number and roughness factor are known as the F can be read off from the graph. So, the forthcoming graph I can show you. So, this is a graph. So, the x axis is the Reynolds number, that is a dV rho by mu, then the friction factor F here. So, Moody chart. So, when the Reynolds number is low, it's always fall in the F equal to 16 by NRE directly. So, here you can see F 16 by NRE, but whenever if you increase the Reynolds number, then this goes to laminar flow to terminal flow, that is the roughness ratio is there, that also we have to account here to calculate the friction factor. We cannot, for a terminal flow, we have to consider both the roughness ratio epsilon by D, then Reynolds number, both we have to conclude. For only for laminar flow, only for Reynolds number is fine. So, that is only they are saying here, the chart shows the low value of Reynolds number, there appears to be a simple relation between the F and RE, it is independent of the roughness of pipes. So, there is a no need to bother about the what is the roughness of pipe. When you go for terminal flow, of course, you have to take that one. So, that is only they are mentioning here, the streamline here flow, there is assumed a stationary boundary layer of the wall. If the stationary, there would be no liquid movement over any, the roughness of that might appear to the wall. So, the friction factor equation, actually the friction factor F, the streamline can be predicted theoretically from the Hagen-Poiseuille equations. So, this part already we know that V z equal to, because last class we discussed V z equal to V max of 1 minus R by R square. From that one, you differentiate this equation with respect to R. Here the variable is R, but this R is a constant. This R is a constant. We cannot differentiate, the R is small r is a variable. So, here you differentiate with respect to dV z by dr, then we get that minus of 2 V max by R. So, then multiply the mu is a viscosity, is a Newton's law of viscosity, we already know that. So, use a mu minus Newton's law of viscosity, you multiply this one, then finally we will get a modification of this one. So, once this one, then we always say this one, it's a Newton's law tau, because always we write tau equal to minus of mu dV z by dr, even the cylindrical pipe or whatever. So, then after that again with some modification, then finally we can get the P naught minus of PL by 2L R, substitute the equation 3 in the 1. So, then finally the F equal to 8 mu by rho R or V after modification, because there is a radius, you convert in terms of diameter, then you get a F equal to 16 by this equation. So, we can write mu by rho dV, we can write 1 by of NRE. So, that is only we are writing 16 by NRE, this only we use for the laminar flow for friction factor to calculate. Clearly, the friction factor is also dimensionless numbers, I already shown. See, here itself again dimensional number showing. So, this is a friction factor F, NRE you know dV rho by mu, and there is a no, that is a dimensionless numbers, there is no unit, because unit will get cancelled. So, from there also we can say that this is the friction factor is the dimensionless numbers. So, friction factor for terminal flow, the next this one. So, normally the terminal flow is not possible to predict the value of F theoretically. So, we need to do the experimentally, have to do some experimental, then only we can check that one. So, in a terminal flow, the friction factors also depend on the surface of the pipe, So, example, rough pipe is there, it leads to higher turbulence than the smoother pipe. The smoother pipe always will give laminar flow sometime, but the rough pipe always leads a higher turbulence compared to this one. So, that the friction factors for smoother pipe is less than the rougher pipes. The ratio of the surface roughness height epsilon, we call it as epsilon by D, we always use the quantify the pipe surface. So, this roughness parameters we will use for the friction factor whenever it is a terminal flow. So, in the practice, the shear stress in the wall by calculating by measuring the pressure drop across the pipe for a given flow rate. So, there is a log plot is there. You can see here this Moody chart. The plot is this is the collection of these F versus RE plots. It's called a Moody chart. It's very easy to find the friction factor for the given flow parameters. So, sometimes what happens if you want to use a friction factor for turbulent flow, the equation called Blaze's equation. If it's Reynolds number for smooth pipe 3000 to 1 lakh, if it is there, F equal to this equation we have to use, F equal to 0.316 by 4 RE power minus of 0.25. So, here roughness can be expressed in terms of roughness ratio, that is defined as the ratio of average height of the projection, but it's available already. Okay, the roughness in terms of epsilon is also meter, and then the diameter pipe also meter. We will get the roughness parameter from here. So, here some tables are given, that is a different type of cast iron or different plastic glass, you just see here. So, here in terms of feet, then other things in terms of millimeter. So, the roughness parameters we have to use for here. For commercial steel pipe, they are using the epsilon is a 4.6 into 10 power minus 5 meters. So, here epsilon is the roughness parameters, then the other one is for, it should be a height in meters, and one other also the meter, diameter also meter. So, there are number of distinct regions in the chart. This is a straight line, if labeled, that is called a laminar flow, that F equal to 16 by NRE. We will always use the graphical representation of Eigen-Poiseuille equation. Wherever if it is laminar flow to turbulent flow, then we have to use the roughness parameter K by D ratio. So, all we have to use here. So, flow through curved pipes, this is again continuation of that one. So, the friction losses are therefore the somewhat greater than the straight pipe, the same length. So, same whatever we discussed in the radius of pipe divided by the radius of bend is always less than 0.02. It gives the, however, the effect of the curvature are negligible. The same Reynolds number again, the transition occurs in the Reynolds number about 8000. 8000 when above 8000, automatically the transitions occur here. So, we will discuss the problems. This is a very interesting problem. So, calculate the pressure drop. They are asking the pressure drop. What is the pressure drop here? Delta P. Pressure drop along 170 meter. The length is a 170 meter. The length is a 170 meter. Then the diameter is a 5 centimeter diameter. We are using the diameter 5 D. Dia is a 5 centimeter. Then the horizontal steel pipe through which the oil at 20 degree, the temperature is 20 degree, is flowing at a rate of 0.1 meter cube per minute. Density is the rho value 910 kg per meter cube. Then the viscosity also there, 84 into 10 power minus 3 viscosity is there. So, what are the problems given here? The flow rate, that is a value Q value, is a volumetric flow rate, not mass flow rate. The volumetric flow rate, so 0.1 meter cube per minute. Then of course, we are converted as a second, because we have to use always SI units here. Then the diameter is a 5 centimeter. The diameter is a 5 centimeter, that 0.05 meter. The length is here 170 meter from problem already given. So, density also there. The density is a 910 kg per meter cube. Then viscosity here it will be available. So, we know the formula is F equal to the friction factor formula, F equal to, we have to use here. So, delta P, diameter, density, velocity, length of the pipe. But here they are asking that what is the delta P. But the problem we do not know value of F also we do not know. Okay. So, delta P, other all values we know. Diameter already is there. Of course, density is there, but velocity we have to calculate. Velocity we can calculate from Q by A. Q by A. The Q is there, already volumetric flow rate is there, divided by cross sectional area, then we will get a velocity. So, all if we calculate, then from there we have to calculate F, then we have to calculate the pressure drop. So, we know already the velocity is a Q by A, because the volumetric flow rate is a meter cube per second, then area is a meter square, then from there we will get a velocity meter per second. We can calculate from here. So, the average velocity V equal to 0.849 meter per second we calculated. Then the for Reynolds number, of course, Reynolds number NR equal to dV rho by mu. So, diameter already problem given, velocity we got it from here, of course density you know and viscosity we know. From there we calculated the values NRE is here is coming as a 460. 460 is a less than 21, less than 2100. So, we always call as a it's a laminar flow, because whenever less than 2100 we call as a laminar flow. If it 2100 to 4000 we call as a transient region, then above 4000 we always call as a turbulent flow. So, now this is very clear, it's a giving, it's a falling in the laminar flow. So, if it is laminar flow, of course we know this one F equal to 16 by NRE. There is no roughness parameters, we no need to use the roughness parameters. We have to use for only just the Reynolds number, then calculate here. So, from there the average velocity, the friction factor F equal to 0.0, F equal to 0.0348. So, the pressure drop here, what is the pressure drop here? The pressure drop, of course we know that one. Now, from there, because F we calculated from here, F we know and density also we know already, then V we calculated from the Q by A, volumetric flow rate this one, then the diameter here. From there we can get the value of delta P, pressure drop. Pressure drop is a 159 kilopascal. So, the person asking here, calculate the pressure drop, calculate the pressure drop. So, from there first we started with the velocity, we calculated from Q by A. Once the velocity done, velocity we know, then we do not know F value we calculated from the Reynolds number. The Reynolds number F equal to 16 by NRE. So, from there, so F you calculated, NRE we have to check first NRE, Reynolds number is a laminar flow or turbulent flow, then only we can do this one. So, in this case is very purely is a laminar flow, what is the friction factor and the pressure drop. So, problem 2 we will move now. The problem 2 again, water at a rate of 200 tons per hour. 200 tons per hour meaning it is a mass flow rate. It is a mass flow rate, it is not a volumetric flow rate. So, mass flow rate always we write a kg per second. To be pumped from a river to factory overhead tank placed at the height of 25 meter. They want to pump from this one to 25 meter of the height of the tank from the river bed. The total length of pipeline is 1.5 kilometer. The length of the pipe is a 1.5 kilometer. The cast iron pipe having an idea of 30 centimeter. The internal diameter is the 30 centimeter will be used for the purpose. The average temperature of water in the river may be taken as a 30 degree. Then the viscosity is a 0.764 centipoise. So, they are asking calculate the Reynolds number. What is the Reynolds number? Then what is the head loss due to friction? They are asking both Reynolds number and this one. So, but here already problem is given, the given F value here, because already is there, we no need to use F equal to 16 by NRE, because already the problem itself, the F friction factor values are already, the equations are already available. So, we can use directly here. So, F equal to 0.014 this one. So, here first what is the mass flow rate, the 200 tons per hour, we cannot use, we have to use everything in terms of SI units. So, convert in terms of kg per hour, then convert finally kg per second. So, this then mass flow rate we have done that one. So, density of water already given 1000 kg per meter cube. If it is not there, you can take, because water is always 1000 kg per meter cube. Then the mu is the centipoise, the viscosity already given. So, viscosity also you have to convert in terms of SI units, that is a Newton second per meter square. So, as usual, now we know V equal to Q by A. So, Q is the cross sectional area of the volumetric fluid. How to calculate volumetric fluid here? We cannot calculate directly, because there is no volumetric fluid. You can see here there is no volumetric fluid. So, only here what we have to do, you know kg per second, then other one is for kg per meter cube. So, make divided this one kg per second and then kg per meter cube. So, both will get, then finally meter cube per second will come. So, you have to take a ratio of mass dot by density, then we get the volumetric fluid, otherwise we cannot get here. Yes. So, here the V equal to Q by A, the Q here the volumetric fluid, that we have to get it from here mass flow rate mass flow rate at is we know already in terms of this one, then density. Both we have to use to get the value of Q, volumetric flow rate. So once volumetric flow rate done, Q value done, then you know area, cross sectional area, that you already know, because already radius of pipe is already 30 centimeter given. So we can use directly, ID diameter is there. So we can use for directly that value. So from there we calculate the velocity is a 0.7 meter per 61. So now we have to go NRE, because whether we don't know whether it's a laminar flow or turbulent flow. So we have to go dV rho by mu. Diameter we know, velocity we know, density is also we know already, the problem already given, then viscosity. You calculate what is the Reynolds number. So once the Reynolds number done, NRE dV rho by mu, the turbulent flow. So then you can use the friction factor equation. That is the friction factor equation, F equal to, so the Reynolds number you calculate F equal to this equation already there, 0.015, 0.125, NRE 0.32. So use the NRE value here and get the value, finally this is a friction factor, F. So once F done, now we have to calculate the head loss due to this one. What is the head loss here? So here we know the F value, of course we know F value from the previous, we calculate this equation, we calculate F value, then L rho V square D, from there we can calculate. So the delta P equal to H rho G, you know H rho G, normally the pressure head this one, H is the height of, rho is the density, it's a gravitational here. So from there we can calculate, you rearrange the equation, then we will get a H. From there we can calculate H equal to 2.25 meter, the head loss due to friction. The problem number 2, first what will happen here, first you convert in terms of mass flow rate to volumetric flow rate, convert the mass flow rate to volumetric flow rate. Once the done, so then we go for velocity, once velocity done, then we know Reynolds number how to calculate. Once Reynolds number done, then the equation, friction factor equation is already available, otherwise you have to use some different equation, whether it's a laminar flow or turbulent flow, but this is following turbulent flow. So once F done, then there is a equation friction factor, the panic friction factor. So then H rho G is there, the pressure, this one, okay. So you just modify, then we will get H of in terms of this one, you substitute all the values, we know the values. Just substitute and get the value of the head loss due to the friction. So next is the problem number 3. It's another one, it's a plan to install a steel pipe with the ID of 20 centimeter, the internal diameter 20 centimeter, to transfer of 1000 kg minutes molasses. Basically the sugar, this one molasses, they want to having a viscosity of 500 centipoise, then the density is a 1.6 gram per density. This line is to be 1000 meter long, the length is 1000 meter, close to 1 kilometer, and then delivery end is to be 5 meter higher than intake. The delivery end is normally the 5 meter higher than the intake. Okay. So they are asking what is the calculate the friction losses if overall efficiency of the pump is 60%, what will be the horse, okay, in terms of horsepower here. So the given this one mass flow rate here 1000 kg per minutes, of course mass flow rate again you have to convert to kg per second. So here because the mass flow rate we have to give in terms of kg per second, the density is there, gram per cc, convert in terms of kg per meter cube, because we have to use only SI units, then mu centipoise, convert in terms of this one. So the elevation difference is a 5 meter, the elevation, because they already mentioned 5 meter that one. The pump efficiency works only 60%, somewhere given already. Okay. The plant install, yes, here 60% of pump efficiency are here. Of course, we know we have to calculate the velocity. This velocity we know V equal to Q by A, and then Q mass, from there we know mass flow rate, then the density, from there you calculate the volumetric flow rate. Once the volumetric flow rate done, then from there cross sectional area you can get the velocity. So once velocity done, we can calculate the Reynolds number. The Reynolds number is here. It shows the laminar flow less than 2100, 2100. So then we can use directly this equation, F equal to 16 by NRE. So once F also you know, so now we know F and L V square G D, then we get the what is the height of this one, H equal to what is the height of this one. So once height is done, we know already what is the elevation of that one already, because elevation is already 5 meter, they mentioned the problem. So, total friction head is the 13.48 meter. I will go back, there is a elevation they mentioned here, because the plant installed the 20 centimeter diameter, but the mass rate is the 1000 kg per minutes, but centipoise is there, then density is there, then the length of the this one is here. So, this delivery end is a 5 meter of higher than the intake, it is a higher than one. So, that is only we are adding the 5 meter. So, the total friction the head is the 5 plus 13.48. So, here same way you convert mass flow rate in terms of volumetric fluid, because we have to calculate velocity. Velocity, why you want velocity? We have to use the Reynolds number. Reynolds number equal to dV rho by mu. So, the velocity we have to use here. So, this once velocity done, then we calculate the friction factor F equal to 16 by Re. So, then if we know and everything we know, then we do not know what is the head. So, total friction, the friction calculation friction head loss here. So, from there we calculated, we got 8.48, already 5 meter is there. So, total friction head is the 13.48 meter. So, now we have to calculate the power equal to P equal to rho g h here. So, here you know because this is a power calculation. So, the height of this one is already available. Then the rho g he, rho is here, then g value, q value is there. From there we got the value of power value 2201 watts. But actually how much we are using here? Only 60% only we are using, 60% of efficiency here. So, then you divide by this one. So, we need actually power required is a 3.67 kilowatts. So, normally we write 1 horsepower equal to 746 watts. So, 1 horsepower equal to here, and you convert in terms of HP, then finally the HP is the how much power required, because they asked in terms of this one, then 4.9 HP, because they asked in terms of HP horsepower. So, that is only we calculated the 4.9 horsepower. Thank you.